Okay, hybridization, here we go, guys. So you got to understand this right up front. We are going to tackle hybridization from two different directions. So we're going to set the stage for hybridization. Why do we even need to think about it? Well, the reason we need to think about it is because it happens. But how do we know it happens? And I'm going to get you to that point. Then, guys, once you understand why hybridization is a necessary concept for us to tackle, we are going to have a very, very practical conversation. And this conversation is going to go like this. What do you need to know for the test? And guys, you're going to find that it is ridiculously simple. Ridiculously simple. All that you've got to be able to do is identify the hybridization of atoms in a molecule. That's it. You don't have to explain it. You don't have to draw it. You don't have to talk about it. You don't have to think. You just got to identify it. And I'm going to show you how to do that really quick. Then, guys, and this is sort of the stuff you guys enjoy, then we're going to call time out. And we're going to have this really weird ethereal conversation about what this looks like, okay? And guys, understand that ethereal conversation is interesting and it explains a lot of stuff, and you're going to have some really interesting connections as you're bringing this all together, and none of it's on the test, okay? So at the end of the day, all you've got to come back to is the practical. If you understand the theoretical, good on you. If you don't, it doesn't matter. Okay? Okay. So guys, setting the stage for hybridization, do not write any of this down. Here we go. So, Lewis dot structures are great, right? They do some things really well. They tell us the structure of atoms and molecules, although they do this in sort of a limited sense. They do this in sort of a limited sense because if we draw something like methane, that's the Lewis dot structure for methane, but we're at the point now that we can understand that there are no 90-degree angles in methane, that this is tetrahedral in 109.5. But that said, Lewis dot structures communicate a lot of information to us. Here's the problem. They don't tell us anything about how covalent bonds form. We understand that there's orbitals that overlap and things like that. But guys, the Lewis dot structures show us what they look like once they've bonded. They don't talk about how covalent bond formation works. So guys, this is where hybridization becomes important. So let me show you why hybridization becomes important. Remember the molecule I just drew on the board, CH4? Given what you understand, that shouldn't exist. Do you see why? Let's talk. So guys, here's what we're going to do. We're going to look at how hybridization happens. So do this. And this is where you want to start jotting things in your notes. So I threw CH4 on the board, and then I just laid out this interesting idea. It shouldn't exist. Here's why. Guys, draw the orbital filling diagram for carbon. In your notes, draw the orbital filling diagram for carbon. Y'all get that? You good? You caught up? Okay. Now do you see why methane shouldn't exist? No? Then draw the Lewis dot structure for carbon. Do it right beneath your orbital filling diagram. Now I'll bet you'll see it. Carbon, no, all elements, let's say it differently. Guys, what electrons show up in a Lewis dot structure? Valence. Which ones are they? Highest S or P. Which ones are those in carbon? How many are valence S electrons? 2 in the S. These guys. How many are in the P? 2. Now do you understand why methane shouldn't exist? Do you see it? How many bonding sites does carbon have as an element? 2. We've got a bonding site here, because remember, we're talking covalent bonds, and covalent bonds involve sharing. Carbon can share these 2 electrons. Why can it not share its S electrons? They're already paired up. And guys, it doesn't have any P electrons down here to share, because it's only got 4 total valence electrons. So in our not fully developed thinking, guys, methane shouldn't exist, because carbon should only be able to bond twice, and it should form CH2 and not CH4. So guys, what allows carbon to form 4 covalent bonds? Now, do you remember when we did this last year in general chemistry? The interesting thing is I'm doing that right now. I did that first period today. So guys, in general chemistry, when you learn to draw Lewis dot structures, you may remember, this is even what it looked like. You may remember when I taught you this, and I had you draw the Lewis dot structures for a selection of atoms. And then I told you, drew carbon last, and then I said, okay guys, here's the deal. You're not going to draw carbon like this. You're going to spread them out, and you're going to draw carbon like this. Do you remember that day? And I don't know if any of you asked the question, but someone always asks, why do they spread out? And I say, I'm not going to tell you. Tune in next year, come back and take AP. Now we're going to talk about it. So guys, why do they spread out? Hybridization. Guys, hybridization explains this spreading out process. So guys, allow me to give you hybridization in a nutshell. Here's the deal. When carbon and other atoms, not including hydrogen can't do this. But guys, when nonmetals, covalent bonds, when nonmetals form covalent bonds, their s orbitals do not form bonds, and their p orbitals do not form bonds. But now you're thinking, wait a minute, we've been told all along that it's the valence electrons that form the covalent bonds, and those are in the S and the P, so we've been told all along that these covalent bonds form with valence electrons, and if they're in the S and the P, how can it be that S and P orbitals don't form covalent bonds? And the answer is this: something mystical and magical happens before these things form bonds. And guys, here's what happens. These valence S and P orbitals, for lack of a better term, mate together. And they have little orbital babies. And guys, here's the thing. The orbital babies that come as a result of this mating together that we actually call hybridization, what happens is the babies kind of look like mom and they kind of look like dad. So what does the S orbital look like? A sphere. What do the P orbitals look like? Figure eights. What does it look like when you smear together a sphere and a figure eight? I'll show you in a minute. But guys, here's what happens. These orbitals smear together and they form, and again we call that smearing hybridization, and when they smear together they form a brand new type of orbital that we call a hybrid orbital. And here's how we draw that. We now have 4 orbitals. The idea is the s orbital and the 3p orbitals marry together and create hybrid orbitals. Now here's the rule. You get out as many hybrid orbitals as atomic orbitals went in. So if you put in one s orbital and 3p orbitals, you get 4 orbitals out. But guys, here's the thing that's interesting. Originally, the s is a sphere and the p's are dumbbell shaped, right? After they hybridize, you end up with 4 orbitals and they all look exactly the same. They kind of look like mom, they kind of look like dad, and we call these things Sp3 hybrid orbitals. So where does the name come from? The name comes from the pairing of orbitals that created the children. So we put in 1s and 3 p's. That's where the Sp3 comes from. If you put in 1s and 3 p's, you get out 4 orbitals and they all look exactly the same. Then here's what happens. These 4 electrons spread evenly throughout those p orbitals, Sp3 hybrid orbitals. Now, how many bonding sites do we have? And that's how CH4 comes together. So guys, if you want to think about this as a timeline, here's what happens. Carbon starts like this. Before this carbon atom can form covalent bonds, it hybridizes. We draw that like this. But the idea is that over here, this is the S, this is a P, and this is a P. And then there's an empty P down here. When carbon covalently bonds, first it hybridizes. When it hybridizes, the S and the 3 P's all mush together, and that forms 4 Sp3 hybrid orbitals. 1 electron goes in each orbital because they're all identical, and now we've got 4 domains with 4 bonding sites, and that allows CH4 to form. So guys, let's answer this question right now. Why does this happen? Why does hybridization take place before covalent bond formation for every element other than hydrogen? Why does this happen? Come on, guys. Why does everything happen? It releases energy. It's easier. It turns out, guys, that this hybridization process is actually an electron loser. If we could draw the energy diagram for this, no, energy loser. Guys, this is an energy loser. Don't write, well, you don't need to write this down. Remember the orbital filling thing that we did? And it goes 1s, then 2s, then 2p. So guys, here's the deal. The 1s orbital, this is energy. So the 1s, then we've got the 2s, then we've got the 2p. When these hybridize, the energy of these 4 hybrid orbitals is actually a little more than the s, but a little less than the p. But because we've got 3 orbitals dropping in energy, these orbitals in total have less energy than the sum of these 4, and that's why this happens. It's energetically favored. And so guys, this hybridization takes place. These electrons spread out, zippy-pow. Now we've got these new hybrid orbitals. And I know you can't picture them, but we've got these new hybrid orbitals. The electrons spread out into them. We call that spreading out, the process of promotion. And guys, these are the orbitals that then form the covalent bonds. Now, what do you need to know? Well, guys, this is all you need to know. We're going to skip through the rest of this. Guys, this is all you need to know. Don't write this down until I tell you. You ready? Here is all you need to know. Don't write this. This isn't even it. So, guys, what is hybridization? Hybridization is the process of mixing together atomic orbitals to form hybrid orbitals, which then form covalent bonds. So now we can answer the question, why can't hydrogen do this? Doesn't have any p orbitals, right? Hydrogen's in the 1s. It ain't got, there is no p orbital in the first energy level. Hydrogen can't hybridize because it ain't got a p orbital. So when hydrogen covalently bonds, it has got just its 1s orbital that shares. But all the other elements hybridize before they bond. Yeah.
So last time we were talking about how some of the noble gases bond, so could helium
No, because it doesn't have a P. So helium,
and helium that can.
correct. But helium doesn't bond to anything. Yeah, helium doesn't go there. But we are going to talk about how the noble gases do this. It's interesting. Okay, so this then is the deal with hybridization. Guys, you got to be clear on this. When hybridization takes place, you get, don't write it down, but it's important. When hybridization takes place, you get out as many hybrid orbitals as atomic orbitals that hybridize. So what does that mean? So guys, what that means is, like, for example, with carbon, we had the S and the 3 Ps. And the S and the 3 Ps hybridized, and we ended up with 4 hybrid orbitals. So guys, you always get out what you put in. Does that make sense? Okay. So guys, with that little bit of information, this is then what you need to write down. Here's what you got to be able to do on the AP test. So everything that follows, write this into your notes. And then it doesn't matter if you don't write down another thing, because everything else we're going to do is just for entertainment purposes. Okay? So what do you need to be able to do? Well, guys, this is the bottom line. Oh, I'm drawing dots. Bottom line is this. You've got to be able to identify the hybridization of an atom in the molecule. So here's the way you do that. Count the number of domains on the central atom. And then make this connection. Those domains are the hybrid orbitals. Guys, for a year and a half, we've been talking about electron domains. Electron domains actually go by another name. They are the hybrid orbitals. Write it down, and then I'll show you what I'm talking about. Are you with me? Can I switch? Okay, so guys, we just said something really bold. Domains, which you guys are very comfortable with, are the hybrid orbitals. So let me show you what I'm talking about by drawing you back to our carbon atom. If you remember, we originally said that carbon should not be able to form CH4 because it's only got 2 bonding sites. And we went through this long conversation about the idea that the S and P marry together, they hybridize, that forms 4 domains, the electrons spread out through those 4 domains. Now carbon, let me draw it that way. Now carbon can create 4 bonds, right? But then you can picture this, right? Carbon goes hydrogen, 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 and it forms CH4. Guys, how many domains are on that carbon in the middle? 4, right? If I had just given you this is how I started, right? If I gave you this and said, how many domains are on that carbon, you'd all say 4. So what's the domain geometry? Tetrahedral. What are the angles? 109.5. You know all this stuff. Well, guys, guess what? Each one of these domains is one of these hybrid orbitals that has 1 electron in it and is then available for bonding. So guys, the idea is that for the year and a half that you guys have been drawing Lewis dot structures and counting domains, what you've actually been counting are hybrid orbitals. So guys, for example, this. What if you had, oh gosh, What if you've got NH3? How many domains? 4. One of them's non-bonding. How many domains? 4. So what would that look like if we were looking at the Sp3 hybrids? It'd be 1, 2, 3, 4, 5. One of the hybrid orbitals is full. The other 3 are available for bonding. Guys, what if we looked at something like water? How many domains? 4. But if we look at the hybrid orbitals, it would go 1, 2, 3, 4, 5, 6. 2 of them are full and 2 of them are available for bonding. So guys, the idea here is that when you're counting domains, what you are actually counting is hybrid orbitals. You get the idea? Okay, so this then is what you've got to be able to do. How many hybrid orbitals are there? 4. So how do we form 4 hybrid orbitals? Well, we take an S and we take 3 P's. Okay? Now guys, watch this. What about nitrite? How many domains are on that central nitrogen? 3. There's 3 domains. One of them is a double bond, but guys, there are 3 domains. And guys, if we have only 3 if we have 3 domains which are hybrid orbitals, guys, this does not come from hybridizing an S and 3 of the P's, because that'll give us 4 domains, 4 hybrid orbitals. How many hybrid orbitals do we have here? Only 3. So how do we explain that? Well, what happened was the S hybridized with only 2 of the P orbitals. And 1 plus 2 equals 3. What happened to the other P orbital? I'll show you in a minute. But guys, this is functionally all that you've got to be able to do to nail this on the AP test. All you've got to do is count domains, understand that domains are hybrid orbitals, and then figure out how those hybrid orbitals were formed. I'm not doing questions yet. So it goes like this, guys. Just write this down. So here's what you got to do. All that you've got to be able to do on the AP test is this. Guys, that's it. All you got to be able to do is identify the hybridization. So how do we identify hybridization? We realize that the number of hybrid orbitals equals the number of atomic orbitals that were hybridized. And guys, I know that that's sort of cryptic, but let me show you, and this is going to make all sorts of sense. So guys, you ready? How many domains can we have around a central atom? Well, 2. What do we call that? Linear. What if there's 3? Trigonal planar. What if there's 4? Tetrahedral. What if there's 5? Trigonal bipyramidal. What if there's 6? Octahedral. Well, guys, guess what? Each one of those structures is caused by a different type of hybridization. So make the connection with me. If there is 2 domains, we call that linear. What type of hybridization leads to 2 domains? 1s and 1p. Write this down, guys. 1s and 1p. That is called Sp hybridization. So guys, all you've got to be able to do on the AP test is this. If you've got carbon dioxide, all right, let's put the electrons on it. Guys, if you've got carbon dioxide, how many domains are on that central carbon? 2. That's Sp hybridized. That's all there is to it. There's 1s and 1p, and when they hybridize, they make two hybrid orbitals. Those are the domains. Carbon dioxide is Sp hybridized. How do we know? There's 1, 2 domains, and 1 plus 1 is equal to 2. Good? Okay. So guys, what do you suppose the hybridization is going to be if there's 3 domains? Sp2. Because now we've got 1s and 2p orbitals, and that adds up to 3. Now, what if we've got 4 domains in tetrahedral? We need an s and 3 p's. Now, guys, what about 5 domains? What about trigonal bipyramidal structures? We've got an S, we got 3 P's. Where do we get the extra domain? D. This is called Sp3 hybridization. Now, guys, what if we've got 6 domains, octahedral, 1 S, 3 P's, 2 D's? Sp3 D2 hybridization. And guys, the bottom line is this. You do not have to understand a stinking thing about hybridization. You're going to in a minute. You don't even understand this yet. Wait till I start showing you things. But guys, all you've got to be able to do is this. Draw a Lewis dot structure for a molecule and then count the number of domains on the central atom. Once you've done that, that becomes the decoder key to tell you the hybridization, because the number of atomic orbitals that hybridize has got to add up to the number of domains. So 2 domains sp, 3 domains sp2, 4 domains sp3, 5 domains sp3d1, and then 6 domains sp3d2. Do be careful, guys. These numbers are written as superscripts. Okay, so given this, and I don't care if you understand this, can you do that? Can you draw a Lewis dot structure? Can you count domains? And can you then convert that into this silly little SP number letter thingy? You okay? Okay, then you're going to nail this on the test. Now you're ready to figure out what this actually all means? Okay, this is cool. Guys, write down whatever you want. I don't care. Because now, guys, we're drawing a line in the sand and we can start talking questions and figuring this out. But again, are you all comfortable that that's all you need to know? All right. So, guys, let's start with some videos. So, what does this orbital baby-making process actually look like? Obviously, this is not what it really looks like. It is an artist rendering of hybridization. Now, guys, I'm going to show you 2 videos. This one's from the book, and then we're immediately going to jump to a website, and we're going to have a different conversation. I'm not going to answer questions about this video. I want it to provide some groundwork upon which we can build on the website. So here you go. Hybridization. S and P orbitals mushing together. This will not include the D's, just the S's and P's.
Hybrid orbitals are formed by a mixing of the hydrogen-like s, p, and d orbitals.
Yes? Mixing together of orbitals.
Characterize a free atom. The 3p orbitals are directed along the x.
You good there? Those are the 3 P's. Where's the S? They'll bring it in a minute. Those are the 3p orbitals. Remember, they look like dumbbells, right?
Y and z axes.
Okay. So now we've got an S and a P. And they are going to hybridize together. How many hybrid orbitals will we get out? 2. Yeah, we put in 1 S and 1 P. Where are the other 2 P's? We'll talk later. But if we hybridize 1 S and 1 P, we will get out 2 hybrid orbitals. What will the domain structure be if we've got 2 hybrid orbitals? Linear, yeah? Hybrid orbitals are domains. So if we get out 2 hybrid orbitals, that's linear. So guys, what do their babies look like? What does it look like if a sphere and a dumbbell mush together? Ready? Here it comes.
Mix an s and a px orbital. We produce 2 hybrid orbitals.
See what happened? Fatter dumbbells. So guys, we end up with fatter dumbbells. So this is 1 hybrid orbital. This is the other hybrid orbital, and what is their angle to each other? 180 degrees, and that's linear. So guys, any molecule like this that is linear is sp hybridized.
Called sp, pointed in opposite directions along the x-axis.
All right, now we've got the s and 2 of the p's. How many hybrid orbitals will we get out? 3. This is called Sp2 hybridization. Check it out.
Mixing of an s with the px and py orbitals produces 3 equivalent hybrid orbitals in the xy plane. We call these sp2 hybrid orbitals.
Here it comes.
Notice that the hybrid orbitals have major lobes which contain most of the electron density in the orbital. These are used in bonding to other...
There we go. So guys, that's what they look like after hybridization. Okay, here's what you got. And we're not going to talk a lot. But guys, remember when we talked about the idea of molecular orbital theory? When you get into molecular orbital theory in college, you'll find out that there is a major lobe, which is called the bonding lobe, and there is a minor lobe called the anti-bonding lobe. Don't worry about it for now. We're going to pretend like these aren't there, because for all intents and purposes, they aren't for us. So guys, what domain structure do we end up with? Trigonoplanar.
atoms. Mixing of the S with all...
So now we got all 4 of them coming together. Sp3 hybridization. How many hybrid orbitals will we get? 4. Tetrahedral. Here it goes.
3 p orbitals results in formation of 4 equivalent sp3 hybrid orbitals, directed toward the apices of a tetrahedron.
And there's our trigonal or our tetrahedral structure. Yeah, behind.
Let's apply the concept of
Okay, so here we go, guys. How many domains on the nitrogen? 4. So what is the hybridization? Sp3, because S and 3 P's adds up to 4.
hybridization to ammonia.
We're going to show it to you.
Here is the Lewis structure for ammonia. There are 4 electron pairs in the nitrogen valence orbitals. We know that an ammonia molecule has a pyramidal shape. This shape can be explained by assuming that the central nitrogen atom employs sp3 hybrid orbitals. The unshared electron pair occupies the 4th sp3 hybrid orbital.
Yeah? Okay. So now, guys, and this is where this is going to push my artistic skills to the limit. We are now ready to talk about what happens to those p orbitals if they do not hybridize. You ready? I'm scared. Here we go.
In the 1930s, Linus Pauling introduced...
Okay, so guys, what we've got here is we've got an animation that shows the hybridization process. And what they're going to do is they are going to show us the s and the p orbitals, but they've broken the p orbitals apart so that they, and you understand this is all happening around the same nucleus, but by teasing them apart, it allows us to see them separated so we can talk about what happens when they don't hybridize. So I actually froze the screen, and we're going to get up here, and this is going to be different. So here we go.
You can click on... Mixing an s orbital with one of the p orbitals generates
So here
2
we go.
equivalent sp hybrid
Reload.
orbitals. Note that the number of hybrid
Reload.
orbitals is equal to the...
Okay, don't reload. Okay, so here we go.
In the 1930s, Linus Pauling introduced the concept of hybridization to explain chemical bond formation. Hybridization is the mixing of atomic orbitals in an atom to generate a set of new atomic orbitals called hybrid orbitals. Click on one of the hybrid orbital buttons to see how hybrid orbitals are produced.
Okay, so here we go, guys. We're going to do sp3 hybridization first. So the s and all 3 p of the orbitals are going to hybridize together. You ready?
Mixing an s orbital with the 3 p orbitals generates 4 equivalent sp3 hybrid orbitals. Note that the number of hybrid orbitals produced is equal to the number of atomic orbitals that are Sp3 hybrid orbitals
The
has a
video or the audio
tetrahedral
gets a little
arrangement.
wonky.
The angles between the orbitals are 109.5 degrees.
But did you notice what they said? They said, notice that the number of hybrid orbitals that are formed are the same as the number of atomic orbitals that went in. So if we do Sp3 again, the S
Mixing an s
and all three
orbital with the three
Ps
p orbitals generates 4 equivalent sp3 hybrid orbitals. Note that the number of hybrid orbitals produced is equal to the number of atomic orbitals that are sp3 hybrid orbitals has a tetrahedral arrangement. The angles between the orbitals are 109.5 degrees.
You good? Okay, so now what we're going to do is let's look at the d orbital hybridization. What does it look like when we have a trigonal bipyramidal structure? Well, that's going to involve the hybridization of a d orbital.
Mixing an s orbital, 3 p orbitals, and a d orbital generates 5 sp3d hybrid orbitals. Note that the number of hybrid orbitals produced is equal to the number of atomic orbitals that are hybridized has a trigonal bipyramidal arrangement.
Does that help? Go
The
ahead,
angles
tell me.
between orbitals are
Oh, hold on.
120
Let the audio
degrees
stop.
in the trigonal plane and 90 degrees between orbitals in the plane and those above and below the plane.
Okay, go ahead. What?
Why does it choose the DZ first?
I don't know. And frankly, I don't even know if it does. Is it Carrie? Is that right? Do you know? Does it necessarily hybridize that DZ orbital? Yeah, Talmadge, I'm not exact. I've never known that. And maybe it doesn't, but maybe it does. I don't know. But we know that one of the Ds does hybridize. So guys, let's go sp3d2. Ready? What's it going to look like? 1s, 3 p's, 2 d's. How many hybrid orbitals? 6.
Mixing an s orbital, 3 p orbitals, and 2 d orbitals generates 6 equivalent sp3d2 hybrid orbitals. The set of 6 sp3d2 hybrid orbitals has equal to the number of atomic orbitals that are hybridized. Between the orbitals are 90 degrees.
You guys good? All right, so now guys, let's do sp2. How can I do this? Hold on. Let me go here and bring up this still first. Okay.
In the 1930s, Linus Pauling introduced the concept of hybridization to explain chemical bond formation. Hybridization is the mixing of atomic orbitals in an atom to generate a set of new atomic orbitals called hybrid orbitals. Click on one of the hybrid orbital buttons to see how hybrid orbitals are produced.
I'm done with the audio. Okay. So guys, you've seen sp3, you've seen sp3d, you've seen sp3d2. What I'm going to share with you now is sp2 and then sp. So, sp2 hybridization. What is going to hybridize together as indicated by the name? One of the S's and 2 of the P's. The question that we need to answer is, what happens to the p orbital that doesn't hybridize? And the answer is this: it's still there. It just didn't hybridize. Let me show you. Sp2 hybridization. We'll give you the audio. Sp2 hybridization.
Mixing an s orbital with 2 of the p orbitals generates 3 equivalent sp2 hybrid orbitals. Note that the number of hybrid orbitals produced is equal to the number of atomic orbitals that are hybridized. The set of 3 sp2 hybrid orbitals has a trigonal planar arrangement. The angles between the orbitals are 120 degrees.
Got it? Now let's talk about that p orbital. You noticed in the animation the p orbital just faded into the background as if it disappears, right? That's not what happens. What happens to that p orbital? It's still there. And guys, it actually looks like this. It is still a p orbital, it is still figure 8 or dumbbell shaped, and it is still present. It doesn't just disappear, it is still there, and it is still a part of the atom. So the question then becomes, what does it do? Now it does, and this is the thing that's cool. Watch. Guys, you ready? Do you see this? We've got an Sp2 hybridized atom, right? So what do each of these green lobes represent? Sp2 hybrid orbitals. What does the blue figure 8 represent? The unhybridized p. You got to understand, I'm terrified, but here I go. You ready? So what does this do? Let me apologize ahead of time. What does this do? Got to loosen up. Here we go. Green. Carbon. That's all I got. So guys, this is an Sp2 hybrid orbital. This is an Sp2 hybrid orbital. This is an Sp2 hybrid orbital. But if it's Sp2 hybridized, what are we missing? This unhybridized p orbital. Now, what does this do? Well, guys, I specifically drew this as a carbon atom because I want to make this one specific molecule. But if we have an atom, a carbon atom, this could be others, but we're talking carbon. If we have a carbon atom that is Sp2 hybridized, it can then bond to another atom. So let me bring into the picture, not now, let me bring into the picture another atom. Here's another carbon atom, and it is also Sp2 hybridized. So now we've got a shared pair of electrons there, and we created a bond. Now we've got another one here, and another one here. And now just let me do this, and these are also Sp2s. So just to keep this as simple as I can, let me bring in, and I'll switch to red, let me bring in a hydrogen atom. It's got a 1s orbital. We end up with a shared pair. Another hydrogen atom, another shared pair, another hydrogen atom, another shared pair, another hydrogen atom, another shared pair. Guys, why does hydrogen not hybridize? It ain't got a p. But this is also an Sp2 hybrid, so we have this unhybridized p orbital right there. You with me so far? So guys, what does this unhybridized p orbital do? Well, the answer is this. It wraps around top to bottom, and it creates a second bond. The Lewis dot structure for this would actually look like this. This is C2H4. We just created a double bond. Guys, that's how double bonds form. When atoms double bond, what happens is this. The atoms that are involved in the double bond don't fully hybridize. P orbitals are held back from hybridization. These unhybridized p orbitals then wrap around top and bottom, and they create the second bond in the double bond. So guys, what we end up with is this. In a double bond, we've got one bond right there. It's in the bond axis, and it is created by hybrid orbital overlap. This is what is called a sigma bond. Then, outside of the bond axis, we have a second bond that is forming. It is not formed by hybrid orbital overlap. It is formed by unhybridized p orbital overlap, and this is what is called a pi bond. Just a moment. So now you're thinking to yourself, whoa, wait a second. Now I sort of see the picture, but how does it tie back to the Lewis dot structure? Well, guys, imagine if you started with this. How many domains are on either one of those carbons? 3. 1, 2, 3. Remember, this is what you've got to be able to do on the AP test. If there are 3 domains, what's the hybridization? Sp2. And this has got 3 domains, so it's Sp2. So notice that the hybridization that we would predict based upon the number of domains then allows for the fact that there's an unhybridized P that creates the double bond. So as we look at this just sort of simply with the Lewis dot structure, we would predict Sp2 hybridization, but that Sp2 hybridization is what is necessary to have the unhybridized P that creates the double bond in the first place. All right, what do you want to talk about? Yeah, let's do that in a second. Because I've got a video of this process that was made by a drug addict, and I want to show it to you. Go ahead.
That's a localized pi bond.
Yes, yes. Oh, baby. All right, let's do it. Yeah, guys, come on. Come on. Let's do this. You ready? This is good. Here we go. Guys, don't draw this, but watch. Carbon, 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 carbon. Hydrogen, 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 hydrogen. How, and then remember what, well, let's just leave it at this for now. How many domains are on each one of these carbons? Come on, how many domains are in each carbon? 3. So what's the hybridization of each carbon? Sp2. So what that means is that each one of these carbons has an unhybridized p orbital. And what do those unhybridized p orbitals do all the way around the ring? They smear all the way around the ring, and we end up with delocalized pi bonding. Do you get it? Guys, that's the idea. Pi bonds, Mark, that's neat that you brought that full circle, no pun. But guys, the idea here is that to create pi bonds, we've got to have unhybridized p orbitals, which is exactly the picture that we've been looking at. Was it page 5.3? Where was that? Oh, it's in chapter 9. Let's look. Yeah, no, don't go there yet. Yeah, all right, let's go there. So yeah, guys, if you look at 355, that's the picture. That if you look in 355 in the middle, they show you the unhybridized p orbitals, and then those buggers wrap all the way around the molecule. If you turn the page to 356, they show you the same thing for nitrate. Those unhybridized p orbitals that are out of the bond axis go in all directions. But guys, think about what we know about nitrate. Nitrate looks like this, right? How many domains are on the nitrogen? 3. So what's the hybridization? Sp2. What happens to the unhybridized p orbital? It goes in all directions at once, and it creates a resonance stabilized molecule. See how that all comes together? Can I show you the drug addict video? I don't know what this guy was thinking, but wow, I wish I'd been there to see it. So here we go. Going back here, where do I need to go? Oh, hold on, not there. Here it is. Well, actually, let me show you this first. I know, right? So guys, this then is the picture. This is the way we think about C2H4. We've got 2 unhybridized p orbitals. Those unhybridized p orbitals wrap around above and below the bond axis, and this entire thing together makes a pi bond. Here's the animation. Good night. Here we go. Ready? So guys, whoa, hold on. I know. So do you see that this is an Sp2 hybrid? Here we've got the 1, 2, 3 lobes that are the Sp2 hybrid orbitals. These are meant to be the hydrogens bonded to those. And then what's the red guy? The unhybridized p orbital. This is almost nauseating. Here we go. Okay, so there we got it. So what is this bond right here in the bond axis? It is a sigma bond caused by sp2 hybrid orbital overlap. Then, guys, the red dudes wrap around top and bottom, and there we've got a double bond. Do you buy it? Okay. So, guys, with that, the question on the table is, what about a triple bond? So, guys, in order to do a triple bond, why don't we do something like diatomic nitrogen? So let's take a look. Guys, we understand, let me use my space more effectively. We understand that diatomic nitrogen looks like this, right? Okay, so how many domains are on either one of those carbons, or nitrogens? 2. So that means this is an sp hybrid and this is an sp hybrid. I'm just going to apologize right now. This is the best I can do. Nitrogen, no, you don't like that. You guys are accustomed to green being hybrid orbitals. Okay, so here we go. One hybrid orbital, the other hybrid orbital. Now, guys, what is in this? And I'm going to draw it here. Let's just do it. Another nitrogen here, hybrid orbital. These are sp hybrids. There's our one shared pair of electrons. Guys, what is in that other hybrid orbital? These guys, the unbonded pairs of electrons. Now, if these are sp hybrids, what's missing from the picture? 2 unbonded, two unhybridized p orbitals. So there's 1 on each, and then changing color, let's go red, and then there's the other on each, but it really should be like this, right? They're 90 degrees out of phase, so 1 up and down, 1 left, 1 up and down, 1 in and out of the board. But then what happens, guys, is these wrap around, so this wraps around with that, and this, oh goodness, this wraps around with that. And guys, a triple bond is 1 sigma bond and then 2 pi bonds. So what does it look like when you're not trying to draw this as some left-handed punk? It's actually not horrible, right? Yeah, so it actually, guys, looks like this. Instead of showing you diatomic nitrogen, this is actually C2H2. But if you were to draw the Lewis dot structure for C2H, oh gosh, I don't know why that didn't work. If you were to draw the Lewis dot structure for C2H2, it would go that's weird. I don't know. Here, let me just draw it up here. I don't know why it won't let me do that. Guys, it would look like this. It would go H, C, C, H. So there's 2 domains on each carbon. That would be an sp hybrid. This would be an sp hybrid. And when we pull that all together, it looks like this. This is our sp hybrid, our sigma bonds, and our pi bonds. You get the idea? Crazy, right? But guys, again, bottom line is you don't even have to understand a word of this. It's cool, and Mark, I'm so glad you brought us around to delocalized pi bonds. Because, oh, and maybe we should say this. Are these delocalized pi bonds? No, they're localized pi bonds. This is a stinking triple bond. But if that p orbital can go in either direction, it will be delocalized. You get the idea? Okay, yeah. Yeah? Are you sure? What are you thinking? Right, exactly. Yep, so that wouldn't work. I'm trying to dig myself out of the hole that I've created. Talmadge, did you want to talk about something? Okay, so guys, here's your homework. But as you're writing this down, let me do this. Now it's going to be this fast. No, no. No, you got to be able to draw. Okay, can we do that? Can I show you? Guys, this is what you got to be able to do. Carbon dioxide. Carbon, oxygen, oxygen, boom, 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 boom. Here's what you got to be able to do on the test. How many domains are on the carbon? 2. So what's the hybridization? Sp. Now guys, what about this? Check this out. What's the hybridization of the oxygens? 1, 2, 3 domains. So what is it? Sp2. What's the hybridization of that oxygen? Sp2. So you guys ready for this? How does this work? Check this out. How many unhybridized p orbitals on the oxygen? If it's Sp2, 1 didn't hybridize. What about on this oxygen? How many unhybridized P's? 1. How many unhybridized P's on the carbon? 2. 1, 2. 1 wraps this way, 1 wraps this way, and you get double-double bonds. So guys, there you have it. Y'all done?